As I mentioned, we selected speakers and the panel specifically based on the topics that have been discussed over the past year and a half. It's really encouraging the quality of the speakers, and I think the first one definitely is one of the quality and one of the individuals that we can say has a significant amount of background in this field. Holland Smith, he's a program lead of analytics and equipment integration at INFICON. He right now leads the smart manufacturing systems architecture and installation projects across many 200 millimeter and 300 millimeter fabs across the world. He's considered a semiconductor data systems expert. Before INFICON, he had a significant tenure at Intel, where he was considered one of the experts in the field of atomic layer deposition. So we really have someone who knows a lot of information and background, both in the area of the fab as well as the data analytics. He comes to us in this regime, and so it's my honor to introduce him, and he's got a great topic for us today on the presentation. So I'd like to hand it off now to Holland to begin his presentation.
Thank you very much for that very nice introduction, Dan. Is my audio coming through okay?
Yes.
Okay, great, thank you. Next slide, please. Okay, so today I'd like to talk about a self-driving fab, what this is, and give a data-oriented perspective on it. So there are three parts. I'm going to provide a definition, and then talk about what are the challenges of automated fab operations, and then what are the types of data you need to address them, and then finally, what are some data architectures out there and potential advances in this area that might be relevant for automated fab operations, and then offer some concluding remarks at the end of that. Next slide, please. So I initially came up with my title somewhat humorously. I hadn't ever heard the phrase self-driving fab before, but I actually think it ended up being, as I thought about it more, a useful analogy to come back to. So I will develop this a bit and refer to it in a few places because there are some interesting similarities between a self-driving fab and a self-driving car. So first I wanted to attempt to define it. So my definition attempt here is a fully automated semiconductor fabrication plant capable of executing to a sophisticated business plan autonomously in the face of dynamically changing conditions. One of the key things to notice here is the input. It's a business plan. So referring to the car analogy, this is like the destination for the car. Like a self-driving car can drive itself safely down the street, but you need to tell it where to go. So that's my current definition of a fab. Once you have a business plan and you know where the fab needs to go from the perspective of business goals, then it can take it from there. But it's not devising its own business plan autonomously yet. So that's how I'm thinking of a self-driving fab. Next slide, please. Next, and one more. Okay, so I wanted to describe the challenge of automated fab operations. What is it like to actually tackle this problem? So a typical factory has hundreds or thousands of lots, and you can think of each lot like a car with a destination. And of course, all the lots have to reach their destination. There are many route choices, and these are sequences of tools that each lot can visit that have varying availability over time on their way to the destination, because tools go up, tools go down. And the way that lots reach their destination must be aligned with core business needs. So some business objectives are going to be impacted by the aggregate motion of all lots, and examples of these are total cost or total time of manufacturing. And then of course, some objectives are going to be affected by the motion of individual lots or through certain critical areas of the fab. So these might be how you deliver on your priority lots, or the number of reticle changes you do in your litho area, things like that. Some business needs will more or less always be true, although their relative importances and weights may fluctuate, and then some may be temporary. And so the challenge is to take this picture and with your business goals, orchestrate all lot movements through the fab so that the goals are achieved. Next slide, please. So I think it's useful to classify goals into three general categories, and I wanted to start with the car analogy because they might be a little bit more accessible. So if you think about one car, let's say you have one car that you need to get from San Francisco to Berkeley. Some example of some global goals you might have are, first of all, you want to get to your destination. You need to get to Berkeley. You probably also want to minimize the time you spend in the car. An example of a local goal might be there might be a shortcut road that could get you there faster, but it has a lot of potholes, so you want to avoid that. And a temporary goal might be, on this particular trip, you need to stop by a post office, though in general you don't. Now imagine you have 1,000 cars and you have to orchestrate them all to do the same thing. Some things you might care about globally are minimizing the average commute time of all cars. You might want to minimize the total gas cost. A local goal might be you don't want to starve or overload bottlenecks. So the Bay Bridge is going to be a bottleneck. You want to make sure you have enough cars on it, but not too few or too many at one time. And a temporary goal across the fleet might be, there might be a temporary air quality alert for the day, and so you'll need to minimize total emissions. So in that case, you'd need to know the emission efficiency of your cars and minimize the commute time for those that are least efficient. Next slide, please. So applying the same categorization to typical FAB goals, I'll go through a few of these, not all of them because there are a lot, but these are the ones we typically see out there amongst our customers. So an example of a global goal for a factory is, of course, meet their targets, shift production targets, day, month, quarterly, as they're aligned with the business plan, of course. Reduce overall cycle time, increase tool utilization. These are general concerns across the entire fab. You might have local concerns that depend on specifics of the area. So one of those might be to minimize setup changes. In the photo area, that would mean swapping reticles infrequently as possible. In your implant area, reducing the amount of time you switch between dopants, et cetera. For your batch tools, you'll really care about batch loading to make sure you get maximum utilization out of them. Some example of temporary goals. So suppose you're a foundry and one of your customers offers you a bonus for meeting a commit early. You might need to instantly prioritize a certain product, or the opposite, perhaps an order is canceled and you need to quickly reduce the way certain lots move through the fab. Another example of a temporary goal, suppose a tool has been identified as unhealthy via some type of FTC analysis, and you want to avoid using that tool for critical lots until the issue is addressed. So that's those are some of that's how you can apply the framework to fab goals. Next slide, please. So in order to tackle these challenges well, you really need a schedule. So a schedule for every lot in the fab at any given moment. One of the requirements of the schedule is that it must adapt to ever-changing conditions, but it still needs to preserve all business goals. I really want to distinguish the idea of a schedule from operational rules, which is how fabs have operated for many decades. Let's go back to the car analogy for a moment. Imagine you do have a self-driving car that's capable of safely navigating streets, and you also have a destination you want to get it to. But instead of giving it a route to get there, you're trying to find a set of rules to get it to its destination. So a really simple rule might be, at any turn, turn right. Now, of course, that's not enough because in a simple city block, that car will be in an infinite loop of right turns all the time. So you might add a second rule. Well, if you come to the same intersection, the next time turn left. Now, with those two rules, you actually can get a car to any destination, but as you might guess, it would take an impractical amount of time. So the key missing element here is the route itself. And that's really what you need in fab operations. You need a schedule, because suppose one of your business goals is, I need 80% of my lots to be on time. Until you start actually placing your lots on a schedule and looking, when are they forecast to end? Are they going to be on time? You can't really quantify whether your approach will reach in meeting your goal. So while operational rules can be written very completely, they can be efficient to execute, they're not a plan. And so a schedule is really that next step of a plan. Next slide, please. I wanted to talk about some of the complications of what a scheduler must do. Certainly not all of them, but highlight a few important ones just to think about. So imagine you've identified your subset of priorities you care about. So you want to decrease your cycle time, lower cost, increase your on-time delivery, et cetera. The first thing you might notice about that is that these objectives have different units. So cycle time is measured in days, cost is dollars, on-time delivery might be the percentage of lots that are on time. And so this is not only a multivariate optimization you need to do, it's a multivariate optimization in differing unit systems. This is something that humans do all the time, although arguably not very well. For example, I live in Portland, and say tomorrow I want to fly to New York. So I start looking at airline tickets. Initially, I'm thinking I want to spend as little time on the plane as possible. So I'm looking only at nonstop flights. But then I see, oh, there's a one-stop option that's available that's actually $300 cheaper. And that really appeals to me because in 2 weeks I'm going on vacation with my family, and $300 is the cost of our hotel for a night. So in this case, that number 300 allows me to compare two very distinct goals for me, minimizing my time on the plane tomorrow and how much enjoyment I'm going to get out of my vacation in 2 weeks. So what I want to highlight here is inherent in a scheduling engine is a currency system. And there's a lot of art involved in tuning that currency system to achieve fab objectives well. The other thing I wanted to point out is even once you've identified your subset of priorities you care about, their weights may vary in time. So that's what these circles are meant to indicate. They can either expand or shrink and get smaller as time goes by. And so a scheduling engine needs to be inherently flexible to not only comprehend priorities, but to comprehend them in different ways at different times. This harkens back to my definition, capable of executing to a sophisticated business plan. If you look up scheduling problems in textbooks, they're often treated as a univariate, simple problem of just minimize the total make span, for example. But in the real world, real factory objectives are often a lot more complicated and the situation's a lot muddier. Next slide, please. One other thing I wanted to highlight is that schedulers control standby time too. Another way to say this is they not only control what happens, but what doesn't happen. And this is really a key observation for enabling a lot of Industry 4.0 initiatives. So we mentioned analytics previously, and a lot of the thrust of analytics is prediction, whether it's yield or equipment events, et cetera. So schedulers can take the fruits of analytics and actually make it actionable. So if you predict that a PM window is required in a few hours, schedulers can actually choose a smart PM window by looking at lots and finding a good time to do it. Another thing they can do is intentionally create blocks of idle time. Why would you actually want to do that? So here's a simple example. Suppose you have 3 tools that are connected to expensive subfab abatement units, for example. So you have a constant, natural gas combustion reaction happening in the subfab that costs you some amount per hour to operate. If you don't have a scheduler and just have dispatch rules ordering lots as they come in a low WIP area, what might happen is represented there on the left. You'll see these 3 lots basically run as they come in across the 3 tools. Now, a scheduler will look ahead and say it knows if it can idle a tool for 8 hours, then it can actually put its abatement unit into green mode and save a lot of money. So it'll take those same 7 lots and schedule them across 2 tools and intentionally idle tool number 3 to create this window to save money. So that's a capability that schedulers enable that rules often do not. Next slide, please. Okay, so I've talked about the challenge of fab operations and the need for a schedule. Next, I want to give an overview of the types of data that go into scheduling. Next slide, please. So I want to highlight the distinction between physical and logical data with 2 somewhat absurd examples. So you can imagine that you can record an arbitrary amount of physical data during a chess match. So let's say for whatever reason during a chess match you install 18 high definition cameras, full-time biomonitoring on all the players, you put pressure transducers under the board, and you put forehead imagers to get a read on their temperatures, and you're collecting gigabytes of data a second. Meanwhile, as the players play, they're generating very little bit of logical data represented there on the right, just a few bytes a minute. Now, of course, if you know anything about chess, all of the problem of solving it from a computer science perspective revolves in the logical data. The physical data could answer interesting questions about human psychology, but it really has no relevance on the quality of the play of the game. That's contained entirely in the logical data. Next slide, please. Here's a different example. Suppose I gave you this drawing on the left, and I said, here's a visual representation of a graph data structure. It's showing some vertices and edges, and you're the red dot. I'm going to give you this controller, and I want you to navigate the red dot to the yellow star. And you say, great, that seems pretty easy. Now I say, and one other thing, that red dot is actually a real car out in the real world as well, and this graph is in fact a real map system. I hope at that point you would have hesitancy about trying to move the red dot. That's because without any physical data, like on the right, your edges could look like that windy road, or they could, like worse, look like this very busy street. So you absolutely need the physical data to safely move this red dot to that star. So driving cars is an example where almost all of the challenge lies in the physical data, the enormous amount of physical data, and the logical data is almost trivial. Next slide, please. So where does scheduling lie? It's actually at the intersection of logical and physical data. Scheduling is an enormously difficult logical problem in and of its own. Without getting too far into computer science, it belongs in the same computational complexity class as chess. In fact, it's NP hard. But you also need physical data in order to do it. It's one thing to say, okay, this lot needs to go on this tool, but immediately you'll ask, well, where is the lot? Where is the tool? How long will it take to get there? Also, what are the RF hours on a chamber on that tool? Because this lot can only run there if the RF hours are less than 45. So you need more than logical data to do factory scheduling. You also need physical data. So another way to say this, an MES alone is not enough. Scheduling requires a high fidelity digital twin. Personally, I try to avoid using buzzwords, and I think digital twin is one, but it's also a very useful one. And I've looked at many definitions, and they're often relevant in the context they're provided in. I wanted to define what I mean by it here. Another way to say this is that a scheduler requires access to physical data recorded with sufficient frequency, information density, and resolution to make decisions about actions, to adapt to changing physical conditions, and to model how the physical system will behave in light of the decisions. Next slide, please. So what are some specific examples of logical and physical data needed for scheduling? So logical examples, you need routing information. So this is the sequence of processing steps for all your routes in a fab. You need what recipes are run at each of those steps. From a whip perspective, you need to know all the logical information about the whip, where it currently logically is, what type of product it is, who's the customer, what's the priority of it, what are the type of wafers, or the engineering production, et cetera. From an equipment standpoint, you need the logical equipment states, E10 availability, capability, which recipes can the tool run, are there any engineering restrictions, et cetera. Skipping to physical information, back in the equipment category, you need actual equipment events. When did the tool actually start processing? What was the timestamp? When did the recipe finish? What is the current setup of the tool and maybe the configuration of the transfer robot? Can it run in parallel or alternate at the moment? You may need to be looking at physical parameters on tools. RF hours is an example I've already mentioned, or tool health, which might be a composite score calculated from FDC data or SPC data, et cetera. I highlighted a third category here, simulation data. This is how schedulers need to look into the future. Now, this isn't really a distinct class, I think, because throughput and cycle time information is calculated from physical and logical data. But I wanted to highlight it as a distinct category. These two pieces of information are how a scheduler is going to know, first of all, how long would it take a lot to get to a certain step? And then once it's at that step, how long would it actually take to process on the tool? So this is a third category that helps a scheduler see into the future, and it's calculated from logical and physical data. Okay, next slide, please. I wanted to do an order of magnitude size analysis of all of this data that goes into factory operations, just to put it in perspective, maybe relative to other industries. And without going line by line, I really just want to point out two conclusions. So on the right-hand column here, I just took an example 500 tool fab, and I put some other assumptions there on the right. But very roughly, a 500 tool fab might generate currently about 300 gigabytes a month of data that's relevant to analyze for automated scheduling. And a huge percentage of that 250 gigabytes alone would come from FDC. Now, of course, there's no single way to set up FDC. This is really just an aggregation of impressions from many different clients. But I think order of magnitude, it gives a good number. And so one conclusion here, press next, please, is that semi-fab is really not Facebook. I mean, you can imagine Facebook with 1 billion users. If each one posts a 5 megabyte photo in one day, there's 5 terabytes of data right there. So we're a couple order of magnitudes off the largest data consumers and stores on Earth. That doesn't mean there is an enormous challenge in dealing with this data efficiently and turning it into actual information. It just means that we're not on the fringe of putting stress on data systems and data architecture. And that's honestly a good thing, because we benefit from work done on those fringes, being a couple order of magnitudes back ourselves. Next slide, please. Just comparing this to a self-driving car, I found this interesting. So 1.5 hours of driving of a self-driving car in 2014 generates 4 terabytes of data. Again, 10 times more than a fab in a month in terms of what's relevant for fab scheduling. Next slide, please. So where do I see these types of data going in the future? So I don't see logical data growing very much. You know, you can always store more, and as fabs run more, history accumulates. And so it will grow slightly, but I don't see any major growth factors there. Now, physical data, I think, as we're all aware of, is exploding. And this is due to many factors. One is increased instrumentation in fabs, new types of sensors, Internet of Things. Also longer data retention times, because as data storage gets cheaper, you can store things longer, which opens up different types of analysis. Integration of new sources that previously may not have been considered operationally relevant, sub-fab data, facilities data, and of course, more replication of original data sources into new data structures in order to do more sophisticated analysis. In terms of simulation data, I'm really not sure. Like honestly, at the moment, I don't see a lot of effort being put in this area. I could see it being useful. But I don't see people running Monte Carlo simulations of 1,000 different scenarios of what could happen in the fab over the next 12 hours, and then trying to draw operationally relevant conclusions from that information. I could certainly see how that could be useful, but at the moment, this is really not a focus that we've been seeing in clients. We tend to be more happy with summary statistics about cycle time and throughput rather than modeling. Okay, next slide, please. The last point I wanted to make in this section is that storing physical data is a very important design choice, and the way to do it well is to understand what questions you want to ask to begin with. So I put an example of four pieces of data on the left there and their sizes, and from one perspective this data is all the same, and from another it's totally different. So the sentence, "the sun set over the mountains at 6:17 p.m." is about 50 bytes. If I read that sentence into my computer and save it, it's about 70 kilobytes. Now I can look at a picture of a sunset that has a timestamp on it as well, and that's 88 kilobytes compressed, or I could watch a 30-second uncompressed high-definition video at 3 gigabytes. Now, what question might you be answering with this data? If your only question is when did the sun set, then you're perfectly fine with the 50 bytes up top. But if you have a complicated question like do coyotes hunt at night, you're going to at least need 1,000 of these images of sunsets and a neural network trained to identify coyotes at the minimum. So the way you store physical data relates directly to the questions you're going to ask of it. Now, this is an important thing for legacy fabs, fabs that have installed data systems over many decades, because decisions may have been made in the past that are worth revisiting now as questions start to change. Next slide, please. Okay, and next slide. So in this third part, I wanted to talk about data architecture and talk about some recent developments, specifically cloud architecture. Unfortunately, in my practice, this section went too long, so I cut out a lot of introduction about what is the cloud, why have we gotten there, and where did we evolve to this point from that. So imagine that I've done that well at this point, and you can certainly read about it, and I included backup slides that are probably going to be sent out. But I'm going to jump straight to the conclusions here of what are the advantages of the cloud and the disadvantages, and how might they be incorporated, going back to this question of scheduling and fab operations. Can the cloud help with this? So some of the biggest advantages of the cloud, of course, it enables large data storage and large computation at potentially cheaper rates. And the reason for this is it allows a separation of usage and metering of storage and compute. So if you need to do some calculation that requires 2,000 cores to run for 24 hours, you can buy that time and those cores. But once your computation is done, you don't own the system, you can turn the bill off. So it opens up a new type of analysis on a frugal model that's really attractive. Additionally, cloud providers have developed a lot of great off-the-shelf data integration, analysis, and development tools, and they're really standardizing a lot of data science tools. Some disadvantages of the cloud, of course, is it's not on site. And for semiconductor factories, this is huge for many reasons. First of all, if you do put any data in it, your bandwidth to your data source becomes all important. Another, of course, are the perceived security issues. It's unprecedented to my knowledge in semi for any semiconductor company to take their important process data and put it in any system offsite that they don't technically own. And then, of course, not owning the bandwidth means it's not suitable for primary critical systems like an MES. It's probably not an acceptable excuse for an MES to go down because you don't own the internet line connected to your data source. Now, there are bet hedging approaches with cloud architecture. Many cloud providers offer what they call an on-prem solution. An example is Microsoft Azure or Cloudera. So they offer their cloud suite, but you build the cloud yourself. You buy the servers, the hardware, et cetera, and install their platform. So then you have all the advantages of their built-in integration tools, their analysis and development, data science tools, but it's still on site and you own it. Now, a scheduler, once it's installed, is orchestrating the actions of the minute-to-minute lot movement in the fab. So it's really a critical system like an MES. For this reason, it's very unlikely to be located in the cloud. However, this does not mean that cloud and big data architecture cannot help with scheduling. Next slide, please. So I wanted to do a thought experiment here and just describe a product that doesn't exist yet, but what it might look like. So imagine there's a product that turns all maintenance events into scheduled ones. It recommends exactly which services to perform when, as needed based on data. So ignore your semi-annual, your annual PM schedule. It will just tell you a short list of what to do as needed. Let's say that this system can guarantee a suitable amount of overall uptime for tools. And it can guarantee a 3-day warn window for all required maintenance. So you're long enough to order parts, find a good time, et cetera. I'm going to go ahead and call this PEPMAN, the Perfect Equipment Maintenance Analytics Network. architecturally, what I would expect this to look like, it would be looking at many different data sources, maybe a 2-year history of operator comments, FTC data, tool service records, tool event logs, subfab data, WIP history. This is something that the cloud would really excel at, drawing from different data sources in different formats. Some of this is structured, some unstructured. It would be terabytes, and do a massive computation on it. But ultimately what it would produce is a very small list, a 3-day PM forecast for all tools, which might be a megabyte or less. And now a scheduler, which lives on dedicated on-prem hardware, not in the cloud, can take this very small result and instantly make it actionable. So the scheduler is massively improved by this huge cloud computation without having to live on the cloud itself. Next slide, please. I'm going to skip this example, so next slide, please. It's basically the same thing because I have 1 minute left. So I'd like to jump to my conclusions here. Okay, final slide. So just to reiterate a few key concepts here. A scheduler is a link between a business plan and automated fab operations. If you return to the car analogy, a scheduler is what consumes logical and physical data to essentially drive the fab to the destination, where the destination here is the business plan. Already, the data and architectures exist to do this very well. And factories do have the data they need to get started. There are certainly advances to be made, both in architecture and data collection, but they're not prohibitive for getting started. Storing data is a decision about what's important. And this is just, again, anytime you store data, you want to think about the question you want to answer with it. In terms of cloud systems, I do see these likely to play a larger role in fab data analysis, but it's very unclear to me if that's also true for critical systems like MES or a scheduler, for example. I see the cloud as a potential generator of insight, but you still need a scheduler to take that insight and make it actionable. Just general advice from installing these across the world, you should always do the basics first, or basics well first. An example of that, I pointed out throughput and cycle time information. This is very difficult to calculate well and make actionable in order for a scheduler to plan well. But all fabs already have the data needed to do it. You just need to spend the proper effort to do it well. I think the existence of new data architecture like cloud platforms likely does not justify new expense, especially for smaller players. I don't see them going out and building a completely new IT centers just so they can have a cloud. I think it's best as done as a replacement for systems that need upgrades or replacement anyways. And then finally, I do want to highlight that assuming the existence of business objectives, scheduling is already at a mature level of efficiency and alignment. And with that, I will take any questions. Hello?
Yes, Helen, thank you very much. Wonderful presentation. Definitely preparing us for the data deluge. We have time for one question, and the question that I have for you is, what are some of the typical data problems that you've seen when installing a factory scheduler?
That is a great question. So I guess I could separate some of them. So some are simply technical. So data might be stored in a system at the moment that's difficult to integrate into something that we need to turn into action. Now this can be solved, of course, by custom code and tools. Another is that scheduling requires high fidelity of the inputs. It's very much a garbage in, garbage out situation. And scheduling may shine a flashlight into areas of data that factories store that they may not be looking at in any other context in a way that's useful to ensure quality. So it really stress tests the quality of many different types of data. And this is something when you do a lot of these installations that you become experts and you learn to anticipate what types of data problems might be lurking and develop tools to quickly identify and refine them. But so data sources is one, data quality is another. But again, none of this is insurmountable, and it gets a lot better with experience.
Okay, well, thank you very much.